Hi everyone, my name is Ivanov. I'm going to talk about precision cosmology with large-scale structure. This is a work mostly done in collaboration with Oliver Filcox, Anton Chudakin, Marko Simonovich, and Matej Zadlaryaga, along with some other people whom you can see in my slide. So our main idea is to use large-scale structure for precision cosmology and to improve the measurements of cosmological parameters with it. And here it's important to mention that the bulk of our current understanding of cosmology has come from the observations of the fluctuations in the cosmic microwave background temperature on the sky. So if you look on the celestial sphere, you can see that the temperature of the CMB fluctuates from point to point, and those fluctuations are random and stochastic. So it's best to characterize them with the correlation functions. The simplest one is the two-point function called the power spectrum. So in turn, this two-point function of the temperature fluctuations is the function of the angular separation, which can be measured in terms of just angles, or its Fourier conjugate the multiple number. And the shape of the CMB power spectrum is a function of cosmological parameters. So now you can fit your model to this data and get the estimates for the parameters of our universe. A very similar picture takes place for large-scale structure. There, the galaxies represent the fluctuations of the density field. And this density field is observed on the sky, but unlike the CMB, you can also measure the redshift of the galaxy. And this way, in fact, you're dealing with a three-dimensional volume of the data. You're dealing with the many images of the CMB, in some sense, many images of the universe, which essentially allows you to measure the density distribution as a three-dimensional function, which now is characterized, it's two-point function. The power spectrum now is characterized by the three-dimensional wave vectors and wave numbers. Well, the wave number is k here, and also the shape of the galaxy power spectrum as a function of k is a function of cosmology, and now you can get the measurements of cosmological parameters from it. Of course, the complication behind this simple story is that the distribution of galaxies is very nonlinear. And here it's instructive to first take a look at the CMB. So if we look at the CMB map, then we'll see the Gaussian distribution, random distribution of cold and hot spots, more or less equal probability of having a cold or cold spots. And then if you keep zooming in, if you go to shorter scales, then you'll see essentially pretty much the same picture, which essentially tells you that the distribution is Gaussian and it can be described by linear theory. However, for galaxies, it's not the case. And of course, on large scales, the distribution of galaxies looks like CMB. It looks like a random distribution of overdensities and underdensities, but as you keep zooming in, you will start seeing some complicated structures like filaments, galaxy clusters, and so on and so forth. So the field becomes very nonlinear and non-Gaussian. The theoretical description of nonlinear galaxy formation, nonlinear structure formation, has been a matter of intense investigations for many decades. And in the end, it has led us to the creation of the effective field theory of large-scale structure, which was put forward roughly 10 years ago. And this theory provides a fully consistent mathematical description of the galaxy formation in the perturbative regime, so that the nonlinear density field can be unambiguously mapped to the linear density field, which was the seat of structure formation. And most importantly, this relation, this Taylor expansion, if you want, it involves some free coefficients, which were called counterterms, and you should think of them as some effective parameters like the viscosity for normal fluids, because we know that viscosity is generated by complicated molecular processes, but in large scales, it's just one number, so you don't need to worry about these processes. And the very same situation takes place for galaxies. So even though their formation is very complicated, on large scales, all the properties of this complicated physics can be encapsulated in a finite number of coefficients, which are called counterterms, and those should be treated as Newton's parameters in the data analysis. All right, so there has been this progress in the effective field theory in other aspects. Now we have fully agreed how the nonlinear description should look like. Let's apply this to the actual data. Let's try to measure the cosmological parameters using this theory. And this took us the creation of a whole pipeline from scratch. And the main idea behind this pipeline is to be able to consistently recompute the power spectrum, the nonlinear power spectrum, as we vary cosmological parameters in the CMB style. So if we define a model, say LCDM, and then we feed the parameters for a set of parameters of this model, we compute the shape of the matter power spectrum and feed this theoretical prediction to data, just like we do for the CMB. And of course, given that this calculation is nonlinear, it's more complicated than just running usual Boltzmann codes. So also it took a lot of effort to be able to efficiently carry out this calculation. And in particular, here we're using the FFT-log algorithm, which allows for fast and efficient calculation of the nonlinear power spectrum. And now we have put all these ingredients, the full nonlinear power spectrum with all the counterterms, bias parameters, all the theoretical features. We have put everything together in a code called class PT. This is an extension of the standard Boltzmann code class, which can be interfaced with standard MCMC samplers like MontyPython, so that you can take advantage of the virtues of this combination. It's very user-friendly. You can easily include new parameters in the model. You can explore various beyond standard model scenarios. It doesn't require any hard coding. If you know how to run class and MontyPython, then it should be easy for you to run our extension as well. So you can find our pipeline online. Please, you're free to use it. Now I'm going to discuss 3 different applications of this pipeline. First is validation with high resolution body simulations. Second, the application to the actual BOS data. And third, I will discuss a forecast for future surveys like DESI and Euclid. So once we have created our pipeline, we validated it by participating in a blind challenge organized by Masahiro Takada and Takahiro Nishimichi. So they have run a large suite of on-body simulations with the total cumulative volume 600 gigaparsecs over h cubed, which is 100 times the BOS volume or 10 times the volume of upcoming surveys like DESI. And all this data is available online. So essentially, Masahiro and Takahiro, they have run these simulations and have measured the galaxy power spectra that corresponds more or less to the BOS galaxy sample, and gave us this spectra, but didn't tell us the correct cosmological parameters that were used to generate those spectra. And the task was to actually measure them. So we applied our code, applied our model, and just fitted this data. So here on the left, you can actually see this data. You can see the monopole and the quadrupole moment of the galaxy, of the redshift space galaxy power spectrum. So here I just remind you that the monopole is the galaxy density auto power spectrum, and the quadrupole should be thought of as the cross correlation between the galaxy density and the galaxy velocity field that you get to observe thanks to redshift space distortions. And it's very important that the velocity distribution is unbiased on large scale, so there is no galaxy bias, and you get to measure the linear clustering amplitude without paying the price of galaxy biasing for this observable. All right, so here you can see the data on the left. You see the data points. You don't see the error bars because they're super small. They're 0.1%. You can see them better on the in the right side, in the right part of the figure. So you see the residual between the data and the best fit. And really, we can fit, our model can fit the data to 0.1% precision within these crazily small error bars. And here maybe, yeah, I should say that not only it's able to fit, but also the optimal parameters that we get from our analysis, really they, within the error bars corresponding to this huge volume, they correspond to the true cosmology. So we're able to recover the true cosmological parameters with 0.1% accuracy from these large simulations. And after that, we got confident in our pipeline and decided to apply the actual BOS data. And essentially we have repeated the same exercise. We took the available galaxy power spectrum measurements from essentially 4 non-overlapping BOS data chunks at effective redshift point 38 and 0.61 two different patches of the sky, South Galactic Cup and North Galactic Cup. And having fixed the model to be based lambda CDM, we fitted the parameters of this model to the data. And having fixed the BBN prior on omega baryons, on the physical density of baryons, we're able to measure all the remaining parameters of lambda CDM, including H0 and omega matter. So omega matter is the current abundance of matter. And you can see that these two parameters, H0 and omega matter, are measured as good as Planck. So here on the left panel, you can see some portion of the posterior distribution of the corner plot from our MCMC analysis with, along with the Planck measurements. And you can see that really the both data is very competitive with Planck in terms of H0 and omega matter. Then we're also able to measure other parameters like sigma 8, the clustering amplitude, or the power spectrum, the tilt of the primordial power spectrum, NS. And we have found that this parameter is very close to 1, which is consistent with the basic inflationist scenarios. So in other words, we got some independent evidence for inflation from the BOSS data. And also we're able to measure the amplitude of the initial power spectrum, which happened to be very similar to the Planck prediction, although with larger error bars. Here maybe I should point out that in all this analysis, we had fixed the model to be lambda CDM, and we used the BBN prior on omega baryons. But if you don't impose this prior, in principle, you can perform the same measurement. You can measure omega baryons from the shape of the galaxy power spectrum. And this way you can derive the constraints on H0 that are independent of the sound horizon. And I think that Oliver Philcox is going to talk more about this in his talk. All right, so where all this information came from? Here in this slide, in the left panel, you can see the matter power spectrum at redshift 1000 after a combination as a function of the wave number. You can see that this power spectrum has a very non-trivial shape. It has a turnover. It has some interesting slope. Also, of course, there are BO wiggles, which we'll know. Then it's also characterized by some tilt, which is not degenerate with the slope. And another feature is the so-called baryonic step, which is generated by the baryons free streaming before a combination. And essentially all these spectral features, they are sensitive to the so-called shape parameters like omega baryons, omega CDM, and NS that can be measured from the shape of the power spectrum regardless of any distance information. And once you know these shape parameters, just like in the CMB, you have the estimates for the features in the power spectrum, and then you can convert the observed angular size of these features into the distance. The observed angular size into the distance using the absolute size deduced from the measurement of these parameters. So you can get the distance measurement. In general, it is sensitive to the so-called volume average distance dV, but in lambda CDM it reduces just to H0. This is how you get to measure H0 from the galaxy power spectrum. And I think that Oliver is going to talk more about this. And then in lambda CDM, the amplitude of the power spectrum is characterized by the combination F sigma 8, because as I told you, only the velocity field is unbiased, and the velocity field is characterized by F sigma 8, but then F is a derived parameter, is entirely fixed by H0 and omega matter in lambda CDM, such that you get to measure sigma 8 without F. And this you can convert into the primordial amplitude as having assumed a model like lambda CDM. Then there is another effect which is unique to galaxies. It's absent for the CB, which is the Al-Kapachinski effect, and has been the main probe of previous large-scale structure full shape analysis. In principle, it allows you to measure in a model-independent way the angular diameter distance and the radial distance of the galaxies, but those measurements are not very precise. And in lambda CDM, for instance, they give no extra information to them. But of course, in the extensions of lambda CDM, this effect can be important. So I have presented all the discussion for lambda CDM, but you can imagine that all these arguments can be repeated for any beyond the standard model scenario. For instance, if you want to change the early physics. Here maybe I should also mention that the standard analysis uses it fixes the shape, the power spectrum shape template, and then and then applies only the Alpha-Paczynski distortions to it, which means that in principle, the standard full shape measurements, say by Bose, they cannot capture the scenario that modify the early universe. And one of them is early dark energy. Maybe you know that this is a very popular scenario which has been put forward to resolve the so-called Hubble tension. And essentially the idea behind this scenario is that if you had some axion-like scalar field prior to recombination, and this scalar field contributed to 10% of the total energy budget at this epoch, then it would be enough to reduce the size of the sun horizon and then maintain a good fit to the Planck CMB data while simultaneously agreeing with the local H0 measurements. But however, maintaining a good fit to the CMB requires shifts of other cosmological parameters. And those shifts are in tension with the Lasker structure data, with the shape of the galaxy power spectrum. So we have done a joint analysis of the early dark energy scenario using the Planck CMB data and the Bose full shape measurements. And we have found that indeed the the region of parameter space that resolves the Hubble tension and which is not strongly excluded by CMB becomes disfavored once you include this data. In other words, the early dark energy scenario, which resolves the Hubble tension, it fails to simultaneously fit the shape of the matter power spectrum, which allowed us to derive the strongest constraint on this scenario to date. All right, let's discuss the future, because we know that there are many large structure surveys coming online in the coming years. So like Euclid or DESI, and we have done a forecast for these surveys, trying to understand what kind of error bars are we going to get from them on cosmological parameters. And I guess the main idea of these forecasts was the following. What if we apply, what if you gave me the data right now? Because we have already the pipeline, we have everything. So what if you gave me data right now? What would be the constraints? So we don't need to build any extra infrastructure. So to answer this question, we have generated the mock Euclid data from the spectroscopic specification available in the literature. And we have run the full MCMC analysis of this mock data using the full nonlinear model and having marginalized over all necessary nuisance parameters. And then we use the same data class as we use now. So we decided to be very conservative in a sense, because of course there are many years to come, and maybe in these years we'll be able to make some progress and make even more improvements. But however, even in this very conservative scenario, we're able to get very strong constraints on the neutrino mass. So here on the left plot, I'm showing you the posterior distribution of the neutrino mass versus the amplitude, the amplitude of the primordial power spectrum, which is these two parameters are very degenerate. But however, with the future surveys using only the power spectrum data alone, you'll be able to break this degeneracy and measure the neutrino mass to precision like 30 milli-electron volts from the power spectrum shape alone. Then, if you combine it with the bispectrum data, in principle, you'll be able to reduce the error bars by 30% down to something like 20 milli-electron volts. And of course, when you combine the full large-scale structure data with Planck, you'll be able to get to the final constraint, which is the 1 sigma error bar equal 13 milli-electron volts. In other words, you'll be able to measure the minimal guaranteed neutrino mass at 5 sigma level. And also, as far as other cosmological parameters are concerned, you'll be able to measure them from the power spectrum data alone as good as from Planck. And importantly, these measurements will have different contour orientations, so that when you combine the contours likelihoods from Planck and the likelihood from Euclid or DESI, you'll be able to massively break these degeneracies and get super tight constraints on the cosmological parameters of lambda CTM. For instance, for H0, you will be able to get a 0.1% precision measurement. All right, let me summarize. I hope I have convinced you that the full shape of the galaxy power spectrum is a very powerful probe, and it already gives you some interesting results and new information about our universe. All this was possible thanks to the developments in perturbation theory, which now is very robust and precise, and can reproduce the data up to 0.1% precision. So having applied all these new ideas to the actual BOSS data, we have found that the current galaxy power spectrum measurements, they allow you to measure H0 and omega matter with precision that rivals that of Planck. And this precision will improve even further in the future with the DESI or Euclid-like surveys. And eventually this will allow us to detect the minimal neutrino mass at the 5 sigma level. And here I didn't have time to discuss some other things that I've been working on, like the covariance matrix. So if you're interested in this, please ask me during the live discussions. Thank you.